Yep. So hi everyone. I'm Blaise. I work at on self-driving cars at Waymo. Got a little bit of help on this one from my son Jonathan over here, who did a lot of the number crunching. And so basically, I'm going to be talking about the effect of the wind on the space elevator, and in particular, looking at the ERA 5 database as a source of data to understand what the wind is really like in the equatorial plane. There's way more on the slides than I can talk through, and so I invite you to go to this link later on if you're interested in staring at the presentation some more. And I'm just going to be breezing right through. So what are we going to be talking about? First, I'll talk about what effect the wind has on a tether. Then I'm going to be looking at ERA 5 wind data. Then we'll have a little look at location selection based on both wind and lightning. And finally, we'll talk about how you can tweak the design of the space elevator to mitigate wind loading. All right, so if you look at a tether that's in equilibrium among various forces, what you'll find is that you have two equations. One of them defines how the elevator tilts under the effect of these forces. And one of them tells you how the tension varies under the effect of these forces. And basically what you find is the normal forces, the ones perpendicular to the tether, are going to make it curve. And the ones that are tangential, that is along the direction of the elevator, are going to change its tension. And in the case of the wind, the curvature is going to be toward the wind, and the force is going to increase toward the wind also, which means that as you start from a straight tether at the top of the atmosphere and work your way down, you're going to become more inclined, and the tension is going to go up modestly. To understand what the forces are from the wind on an elevator, I use the cross flow principle, which applies in certain cases. What this principle says is you can take the velocity of the wind and split it up into the normal and tangential components, and compute the effect of each one of those independently, and then combine them to see what the effect on the elevator is. In this case, what we're going to find is that there's a normal load on the elevator that's essentially the load that you would get from normal wind times cosine squared. And then there's some other terms that go like v to the 3/2, which we'll ignore. Tangentially also, we have terms that go like v to the 3/2, which we'll also ignore. And those v to the 3/2 come from v squared divided by the Reynolds number. If we combine the results from the two previous slides, we get a differential equation that gives you the shape of the ribbon. You can integrate that, and you find that the inclination at the base of the ribbon is some function of VRMS divided by V critical. So what are all those things? VRMS is basically the square root of the average, the square root of the average of velocity squared integrated over pressure. So it's really this equation here. You want to think about it as a measure of the average wind speed, and it's the right measure that is going to make the formulas work out. The critical velocity depends on the tension in the tether, various parameters like gravity and pressure, and the width of the tether. Or you can swap it over, and instead of tension and width, it's stress and thickness. Then the function f is this somewhat complicated function that looks a lot like x squared for the most part. We can plot it over here. On the x-axis is the ratio, VRMS over V critical. And here on the y-axis, we have the inclination. So the inclination increases. And after a while, we get into a zone where some of the assumptions I made start to break down, and you don't want to trust these curves too much. What is the critical speed, VC, for the reference design space elevator? Well, it turns out that it's about 9 meters per second when there's no climber. And then once the climber starts climbing and you are in a low tension region below the climber, I'm assuming, say, 10 gigapascals, now it's more like 3 meters per second. These numbers will definitely vary depending on the design of the elevator, but this is just to kind of give you an order of magnitude when we start looking at ERA 5 data. What's an acceptable inclination for the tether? Well, I would see two different criteria. The first one I call load fraction. As the tether becomes more and more inclined, the vertical component of the tension becomes a smaller and smaller proportion of the total tension. You know, there's going to be a cosine theta factor that will make the tension decrease, the vertical tension decrease as you incline the ribbon. So if you want to have most of your tension available for lifting the climber, you're going to have to keep that load fraction pretty high, keep the inclination low. So this plot tells you, as a function of the ratio of VRMS over VC, what the load fraction is. When you're less than 0.5, you know, it makes almost no difference. After 0.5, it starts to matter. And at 0.68, you reach 90% load fraction. That's the magic number I'm going to work with, but you're welcome to choose a different one. The second thing to worry about is pull down. If you have enough wind that your elevator tilts and tilts and tilts and gets to 90 degrees, once you get to 90 degrees or close to 90 degrees, you're essentially going to get in a situation where the ribbon just kind of rolls itself down onto the ground. It's going to be pulling down on the counterweight. The counterweight will start to descend. That will reduce the centrifugal force on the counterweight, which will further reduce the tension and just make things worse. So, you know, once you get close to 90 degrees, bad things are going to happen. You want to stay away from that. I'm going to go to 70 degrees, and that corresponds to a ratio of 1.32. So there's been earlier work in this direction. I invite you to read this after if you're interested. I'm going to skip right on to the ERA 5 database. This is a database put out by the European Union. They basically have a model of the atmosphere. They constrain it with the actual measurements that we have of the atmosphere. And this basically allows them to produce a prediction of what the atmosphere state is across the whole world. They provide this for the time range from 1940 to present in a resolution of 1 hour and 0.25 degrees. That's about 28 kilometers. They have 37 pressure levels going from the ground up to about 60 kilometers. And this data set includes several data products, including the ones I'm interested in, which are horizontal and vertical wind velocity. For this analysis, we collected data for the whole period on the equatorial region with slices every 3 hours. And it's a data set that's about 100 gigabytes in size. This is probably the most important plot that comes out of our analysis of that data set. So what this tells you is, for various percentiles, what the RMS wind speed is as a function of longitude. So for example, if I look at this top plot, this is the maximum RMS speed ever seen in the ERA 5 database. If we go down a few lines, this one corresponds to the 90th percentile. So 90% of the time you'll be below this RMS wind speed, and you know the other lines are similar. What do we see? Well, the continents definitely have lower wind speeds than the oceans. The middle of the Pacific is about the worst place you can go for wind. You know, people call it the Pacific, but you know, from the space elevator point of view, that is not accurate. Brad Edwards was placing the elevator 1,000 miles west of the Galapagos Islands, and that was supposed to be a place with very low wind, but it doesn't really look that way in this plot. And so we tried to figure out what was going on here. This is the plot from the NIAC report. And if I plot the wind speed as a function of altitude and look at what's going on at ground level, that actually matches this plot pretty well. However, if you look at the pressure caused by the wind, you know, it's highest up at, you know, 10, 15 kilometers. And so while, you know, there might not be much wind at ground level, 1,000 miles west of the Galapagos, you really need to be looking higher up to determine what the deal is. And, you know, there is a lot of wind there. Here I've plotted a band around the equator, just to give an idea of, well, the fact that the equator is actually a very calm region compared to higher latitudes. You know, once you start getting past, once you start getting past 10, 15 degrees, the winds get quite a bit stronger. Here's just a picture of the whole Earth, if you're interested. All right, this data set goes up to 60 kilometers. When you look at the distribution of wind as a function of altitude, you actually find that it would be nice to have a little more height than that. We're definitely declining in terms of forces on the elevator by the time we get up to 60 kilometers. But I wouldn't be surprised if there was, you know, maybe a 10% error still left with the data we have. We can also look at the vertical component of the wind. I won't say much here other than above 20 kilometers, there isn't a whole lot going on. Near the bottom, you can get some pretty high wind speeds, but they are extremely rare. And for some reason, they're more in the upward direction than the downward direction. If you do a cross-section through the atmosphere, this is just at January 1st, 2024, what you see is you get these very localized regions of updraft, and then much more spread out regions where downdrafts happen. I presume that a meteorologist would look at these and know exactly what's going on. The important thing for me is that these fast updrafts aren't actually that much of a problem because they will tend to curve the ribbon towards being more vertical. And so for us, they're not going to be a big challenge. If you plot wind direction versus altitude, you find that there's all kinds of interesting stuff going on. This is just a plot as a function of time for some location, might be the Galapagos, I forget what I picked. And so one thing this tells you is, the VRMS numbers I've been looking at are actually pessimistic because they don't consider the fact that the wind will be coming from several different directions. And in practice, that will reduce the effective VRMS that we should be working with. So that's placed for future work. There's other studies we can do. We can look at the seasonality of the wind. Pacific has more in the winter. Indian Ocean has more in the summer. We can look at how different years compare. So there's definitely some outliers. Maybe up here in the Pacific, down here in the Indian Ocean, and then this event in 1983 that I looked at a little bit more. That particular event lasted a few weeks, and it looked like what happened is that the subtropical jet stream got disturbed by some weather events that were going on and ended up down in the equatorial region, where we had this mass of fast-moving air at the subequatorial jet stream altitude. There's some videos that you can look at if you download the talk. I will not have time to show them now. So where should we put this space elevator if we want to take into account wind and lightning? So here we've got the plot I showed before zoomed in with the distribution of wind. Here I've taken a map from Vaisala that shows lightning distribution. And so in the case of South America, there is a region south of Suriname here that has relatively little lightning. But other than that, your best bet is probably to go out in the ocean, probably staying close to land because that's where the winds are lowest. Similar deal in Africa. Kenya has relatively low lightning distribution. But other than that, you're probably best off going in the ocean on either side, where the wind speeds haven't picked up too much yet. If you look at Indonesia and surrounding islands, there's lightning all over the place. So here you're probably going to want to be in the ocean on the eastern side. And so if I was China, this is probably the area I'd be looking for to build my space elevator. All right, let's talk about how we can adjust the elevator design to mitigate wind loading.
1 minute.
1 minute, okay, I'm going to go slightly over, I think. Here we have a situation where we're trying to launch a climber. The climber is going to start at the bottom. There isn't too much inclination in the ribbon. It climbs up, but as it climbs up, the tension below the climber is lower, which means that this moderate wind we had now it leads to excessive inclination. There's a problem. Now we'll look at another situation in which we're talking about survival conditions. Here we have particularly high wind conditions, and there's no climber, but the wind is high enough that we're going to end up with excessive inclination. How do we deal with this? We can do what I'd call reel-out launch. This has also been called spring forward in the back, though I've never really understood that name. In this case, what we do is we have a spool of narrower ribbon down below the climber. We let out that spool, and the climber rises. And once we've let out a whole atmosphere worth of spool, the climber then actually starts climbing. Now in the atmosphere, we have this much narrower tether, and the moderate wind is no longer able to cause excessive inclination. Similar in survival conditions, we can unspool that narrow tether and remain with acceptable inclination despite the high wind. So if you want to design a space elevator, start by giving yourself a spec. So I say I want to launch when the wind is less than 15 meters per second. That's about 90th percentile, so we could probably build a business around that. Above the climber, I want to have a 90% load fraction. Below the climber, I want inclination less than 70 degrees. For a survival spec, I'm going to say I want 30 meters per second of wind with an inclination at 70 degrees. So I'm going to use this plot over here that's basically a refactored version of the plots I showed earlier in the talk to design the elevator. Here I have load fraction and inclination. And down here I have the width of the tether divided by tension. That's a little bit unwieldy to think about. And so up here, I've placed another axis in which I have the width of the tether at 20 kilonewtons or 200 kilonewtons. And then I got various lines here that correspond to different wind speeds. All right, so let's design a climber. I want to be able to have a 90% load fraction at 15 meter per second wind speed. If I read up, this tells me that at 200 kilonewtons, I'm going to have 42 millimeters, a ribbon that's less than 42 millimeters wide. Below the climber, I want to have at most 70 degrees inclination, still 15 meters per second wind speed. That means I have to have a ribbon that's narrower than 16 millimeters. Similarly for survival, now I read over to the 30 meters per second line, and I have high tension, and so I'll read off here that I need a ribbon that's less than 40 millimeters. So in this case, I don't actually need to do anything special for my survival spec. I don't have to raise the thin tether. The thick one that the climber can climb is big enough. Now, if I say 40 millimeters, a lot of people will get unhappy with me and tell me that that's not climbable. Indeed, if you look at the ISEC climber tether interface study, they look at the stresses in the rollers of the climber, and they find that they're at about 50% of the yield strength. So clearly, if I move the ribbon from 30 centimeters wide to 4 centimeters wide, I'm going to destroy my rollers. For me, the clear answer here is we don't want to use a pinch drive. We want to move to a capstan drive. In a capstan drive, the tether is in contact with the rollers over a much larger arc. This reduces the pressure in the rollers, and this should allow us to go from a 30 centimeter tether down to a 4 centimeter one without breaking the rollers. The little concept I have here is a kite survival mode. Let's imagine that there's very high wind conditions to the point where even my narrow tether is seeing excessive inclination. Well, I could let up a kite. This kite will have some drag, which will cause an inclination step change, but it will also have some lift, which will increase the tension in the lower part of the ribbon and allow the inclination to maybe remain acceptable. Lots that we haven't really considered here. One of the most important ones is we've assumed that the ribbon is perpendicular to the wind. If we could ensure that the ribbon is always going to be edge on, we get a 100x reduction in wind loading, and that would completely be a game changer. So, are there ribbon features we could engineer in to encourage the ribbon to align itself with the airflow? Other consideration, the ribbon stiffness is very low. I'm worried that there will be aeroelastic effects that could cause flutter. This could increase the effective drag. It might create some dynamic loads that are a problem. And another issue could be, if you start twisting the ribbon, as we'll see tomorrow, it can undergo lateral buckling, which might cause damage. All right, that's pretty much all I wanted to present. No need to go over these conclusions. They're essentially what I've already talked about, and so I'll switch straight to questions.
Thank you. Jim.
Well, Blaise, I'd like to volunteer you to provide a module and that interfaces with the atmospheric database that I can supply longitude, latitude, altitude, and maybe date, whatever you need for the time or date, time of day and date. And you can provide the vector for the wind and the air density. And I can then incorporate that into my simulator. I do have a simplified atmospheric model that's currently in the simulator, but it's not as accurate as the one you have available now. And then I can return the simulator with an example tether, for you then to do the permutations of how you want to deal with the the wind loads and how to mitigate it with like the pull down and all the other factors you have on your report here.
I'm not sure I have that much value to provide there, Jim, because you can just go to the Aero 5 website and download this data. It is kind of unwieldy, as you as
Well,
you can see.
that's the thing is you've gone through the learning curve of learning how to wield the unwieldy data and that, and I'm hoping to eliminate some of that time.
Yeah, but all
You know,
the effort is going to be in the interfacing it with your software. I mean, it just gives you an X data array, and you can load it into whatever.
okay.
So there's not a whole lot of extra value there.
Okay, then if you don't mind a few emails or Zoom
I would be
exchanges to get me up to speed, then I'd be glad
absolutely.
to do that.
Yep, totally.
Yep. Paul?
Did you look at the difference between the ribbon being flat and a cable, which is round, in a wind? Because it seems like a round cable, the wind would go around it a lot easier than a flat ribbon cable.
Yeah, so you're saying, can we basically go as narrow as it possibly can, which would be a round cross section? That will be even better than 4 centimeters. And yeah, I think we'd be fine in that situation. I think their climbability becomes even more of a concern. Maybe a square cross section would be the way to go. I don't think we've really pushed on how narrow the capstan drive can go. And so right now I'm focusing on 4 centimeters because that will give the least shock to people who are used to thinking that 4 centimeters isn't climbable. But yeah, it's quite possible that you could go down to 3 or 4 millimeters, and that would further reduce the loads, and maybe move you away from situations like the one in this AI generated image, which, while they look kind of horrendous, are actually not that bad. We're not at the 70-degree inclination that I'd be comfortable putting the elevator in.
Okay, well, thank you very much.
Great picture, by the way. It looks almost gothic. Stephen, quick question, and then we'll go on.
Yeah, Blaise, you mentioned the edge on Flutter. Is that going to be a future study for you?
Maybe, though that's a very challenging one. So I don't
Yeah.
know. I've started looking a little bit, but I haven't quite figured out yet how to do something that I will myself believe in. This is the type of thing where you probably do want to be doing a lot of work in wind tunnels and things like that, and so it makes it a little harder for an amateur to pull off. But I'm definitely scratching at the surface and trying to see if there's a nugget there I can pull out.
Well, I think that'd be a very challenging thing to do.
Yes.